For the first question, we're asked to provide the Iupac name for the following compounds. So for this, we have our parent chain, which is a 1, 2, 3, 4 carbon chain. We have a methoxy group, so a methyl group, CH3 connected to an oxygen at carbon number 1. At carbon number 2, we have a methyl group. So this is going to be 1 methoxy, 2 methyl butane, and we have a stereocenter here, which is at carbon number 2, but there's only one stereocenter, and what's attached to it is a hydrogen that isn't shown that I've drawn in. And for ranking what's attached, we've got this one's ranked first, CH2 beats CH3, that says an oxygen attached. This one has a methyl group attached, that's 2, that's 3. So we've got a clockwise rotation. So this is R1 methoxy, so 1 methoxy, 2 methyl, and then 1, 2, 3, 4 carbons, butane. For the next one, we have 1, 2, 3, 4 carbons again. So we have butane. This is going to be butanoic acid, and that's carbon number 1. At carbon number 2, we have another methyl group. And for the stereocenter on this, for what's attached, we've got that ranked 1. Our ethyl is ranked 2. Our methyl is 3rd. And our hydrogen is 4 in the back. So looking at the rotation, that's an S stereocenter. So this is 2 methyl, butanoic acid. And this is, like we said, an S stereocenter, so S 2 methyl butanoic acid. And for this compound, we have 1, 2, 3 carbons, and we have an amide functional group, and we have 2 methyl groups attached to our nitrogen. So this is going to be N-dimethyl, and then we have a 3 carbon chain, so propane. If it was a 3 carbon chain, but we have an amide functional group, so we take off the E and add amide. All right, for the next question, the following epoxide was exposed to ethanol. So this is our epoxide functional group. It's exposed to ethanol under acidic conditions. So we've got acidic conditions, and we've got ethanol, ETOH, as our reagent and solvent. Show the mechanism and predict the stereospecific product. So in the first step, we're going to do a proton transfer. So our epoxide will be protonated. So drawing our 5-membered ring, we have our epoxide, which is now protonated, the hydrogen, and that methyl is still there. Under acidic conditions, once that's protonated, it weakens this bond here, meaning we have a more substantial partial positive charge on this carbon. So that is what our weak nucleophile is going to attack. So our ETOH is going to do a nucleophilic attack on that carbon, and that's attacking from the back side. So essentially it's going to push this methyl group up a little bit, and definitely more towards the front, or more towards you as you're looking at the screen. That pushes that, breaks that bond, pushes those electrons up there. So that gets us to our next intermediate, which is our 5-membered ring. And now we have our alcohol functional group formed. That stays on the wedge that it was on. That bond never broke. And now we have our ethanol attached. That's going to now be on the dash. And that ethanol is still protonated, a plus charge there, and an ethyl group. And now my methyl I'm going to draw as a wedge. All right, in the final step, we need to do a proton transfer reaction. So ethanol is our strongest base in solution. So that can take that proton, get there, that gets to our final product, which is alcohol functional group and methyl group there, and our oxygen bonded to an ethyl group there. So I explained here, so once you protonate your epoxide, you have a partial positive charge on the more substituted carbon. So partial positive charge on more substituted carbon, meaning that's the electrophile that our weak nucleophile can attack. For the next question, the following epoxide was exposed to ethoxide, which is the deprotonated form of ethanol. So looking at ethoxide, we have ETO-. Sometimes within the chapter, this was presented as ethoxide in a solution with ethanol, which is reasonable. If you want to write that, or write ETOH, or write out your ethanol, that'd be fine too. For this, show the mechanism and predict the product. So in this case, the mechanism is a little bit shorter. We're going to attack the less substituted side and break that bond there. That gets us to our intermediate, which is our 5-membered ring. And now we have our oxygen, or our oxide anion, on a wedge over here. This bond broke, but now what we have attached to that is our oxygen with an ethyl group attached to it. And we still have our methyl group, which is still on a dash right there. And if you didn't draw in ethanol and didn't use that as your weak acid, that'd be fine. If you just drew in HB, that'd be fine too. So either one works, whatever proton you draw would be accepted in this case. So we're going to take that proton, move the electrons to form its conjugate base. Once we protonate that alcohol, we actually have the final product. So I'm going to just draw it up here. So we have our 5-membered ring, and our O-ethyl group is on a dash on that carbon there, and we have our alcohol functional group on a wedge, and we have a methyl group on a dash. And just double checking, we've got a 1, 2, 3, 4, 5 carbon ring, so our pentane ring, cyclopentane ring, is still there. Alright, for this it says we need to draw ethanoic acid, ethyl ethanoate, and ethanamides. So, and briefly explain why this is the most reactive. So drawing the next, we have ethanoic acid, which is the same as acetic acid. So we have our carboxylic acid functional group and ethyl ethanoate. So for our ethyl ethanoate, we have the ethane part of our ethanoate here, and then we have an ethyl group attached to the oxygen of our ester functional group right here. And finally, ethanamide. So we have our still carbon-carbon bond attached to the carbonyl carbon, and we have a nitrogen attached. We haven't specified any substituents on the nitrogen, so this is going to be 2 hydrogens there. This is in order of reactivity right here, and specifically this compound is the most reactive because Cl- is the best leaving group. And specifically it's the best leaving group, it's the most stable conjugate base. So thinking about our leaving groups here, our hydroxide anion is about equally stable as our oxygen with a negative charge. Our alkoxide anion, both of those are slightly more stable than our nitrogen anion, so that chlorine is by far the most stable conjugate base. It's the best leaving group. That's why it's the most reactive. Also thinking about electron donation and the attack on our carbonyl carbon, since that chlorine is such a stable conjugate base, since that chlorine wants those electrons so much, there is more of a partial positive charge on the carbonyl carbon there than there is on the carbonyl carbon here. So that partial positive charge is more prominent. Our oxygen is able to pull more electron density. The chlorine's not donating electron density, where here, even though the oxygen can pull electron density, essentially it's going to be stabilized by the donating of lone pairs on the oxygen here. All right, for question 5, draw acetic acid and bleach as the starting materials of an acid-base reaction. So for acetic acid, that's the same thing as ethanoic acid. Acetic acid is just the common name, and you're given the formula there. And bleach plus NaOCl as the starting materials of the acid-base reaction. Show the proton transfer reaction. So our electrons from this oxygen are going to take that acidic proton of our carboxylic acid functional group to give us our deprotonated carboxylic acid, which is a carboxylate anion, plus HOCl. Label starting materials as acid or base, so that is our acid. That's what's giving up its proton. This one is our base. That's what's taking the proton. And then we have our conjugate base and our conjugate acid. All right, in the next question, propanol was exposed to the protonated form of bleach. So the protonated form of bleach is our HOCl. And propanol is propane, so a 3-carbon chain with an alcohol functional group. So if this reacts with our protonated form of bleach, HOCl, we'll do a proton transfer reaction there, put those electrons to form the conjugate base. That'll get us to our next intermediate, where now we have the protonated form of alcohol, which is a good leaving group, which is water, and we have our OCl. We have the conjugate base of this reaction, which can now do a nucleophilic attack on that carbon to kick off that leaving group, giving us our next intermediate, which now we have OCl attached, and it's more convenient to just draw out the bond between that oxygen and chlorine, because next we're going to do the equivalent of an ET reaction, and that will get us to our final product. So for this reaction, we need to use a weak base in solution like H2O and take one of these 2 protons, form our double bond, and kick off our leaving group. We formed an aldehyde functional group. So for predicting the product of the reaction, we have our aldehyde functional group there, so that is the main product of the reaction. So the name of this compound is propanal, which we'll look in the next chapter. So we take off the E, add an Al for the aldehyde functional group. Briefly explain why the carbon is not fully oxidized. So we did not form the carboxylic acid. So carboxylic acid formation didn't happen because we didn't use a strong oxidizing agent like H2CrO4. So we used the weaker of the oxidizing agents that wasn't able to fully oxidize this carbon like the stronger oxidizing agent, H2CR4, would have done. All right, speaking of that strong oxidizing agent, chromic acid, this says propanol was exposed to chromic acid. So for this, we have propanol again that's exposed to chromic acid, H2CrO4. Make the formula of reagents, predict the product of the reaction. So in this case, if we fully oxidize that carbon, now we have a carboxylic acid functional group. And then that is basically the strongest oxidizing agent. So it's going to not stop at the aldehyde, we're going to take it all the way to the carboxylic acid. All right, for this one, if you use terbutanol as our starting material, and we react that with chromic acid, H2CrO4, there is no product for this reaction, so this is going to be no reaction. And this basically told us that there was going to be no reaction when it says explain why the carbon wasn't oxidized. And the reason why is because there's no hydrogen to take here. So when we looked at that mechanism back here with bleach, you have to be able to take that proton to form your carbon-oxygen double bond to oxidize that carbon. If there's no proton to take to oxidize that carbon, then it's impossible to oxidize. That proton isn't there. I don't want to be misleading there. That's not there. We already have 4 bonds, so there is no proton there to take. So no available hydrogen to take. For the next, predict the products and starting materials of the reaction. So in this case, if we've got an acid and we have an alkene, we're going to protonate our alkene. Now this is going to form a very unstable intermediate. So basically now we have CH3 and a carbon with a positive charge. Water can come in and stabilize that carbocation, and then we can do one more proton transfer, and that's going to get us to the compound ethanol. So an oxygen attached to a carbon, which is attached to another carbon. So we've got ethane, and then we have an alcohol functional group, so that is ethanol. In this case, if we have a strong oxidizing agent, we're going to fully oxidize this ethanol into acetic acid. For this reaction, this is one of the more challenging ones on here. So thinking about how we could form this, sometimes it's better to go stepwise, basically backwards. So go basically from the product to 2 to 1. So in order to form this, if we have this reagent here, then we need to have something like this. So we need to have our oxygen be nucleophilic, so we can add this propyl group to it. So something like this would be good if we know we have this reagent, because we can do a nucleophilic attack, basically an SN2 reaction on that to kick that off, so we can form that product. Now the question is, how can we get to here? So this is our intermediate. What starting material could we use and react it with this base to get to here? Well, the answer to that is a carboxylic acid starting material. So we would want to deprotonate our carboxylic acid first with our sodium hydride. Once that's deprotonated, then we can react it with our alkyl halide to convert our carboxylate anion into an ester. So in this case, we've got 1, 2, 3 additional carbons, 1, 2, 3 additional carbons on our carbon chain. So our starting material here is butanoic acid. For the next one, if we have an ester and we have 2 equivalents of our diethylamine, so 2 ethyl functional groups, and we have 2 total equivalents of our diethylamine, we can convert this into our amide functional group. So in this case, we'd have our oxygen and our nitrogen has 2 ethyl groups attached, so that's going to have 2 ethyl groups attached. There are 3 bonds, a lone pair that's neutral now. So we would, in one of the steps, so there are 6 steps to get here, we would deprotonate that hydrogen to get us to our amide. All right, there are actually a few options here, but essentially if we have a carboxylic acid derivative, I would say if you put your acyl chloride on here, that'd almost be too easy. We probably wouldn't even need this. You could just add water to it and that would transform it to this. So probably something less reactive would be a better option. I'll see what I see and probably accept a few more, but if you have an ester functional group, that would work. If you put an amine there, or sorry, an amide functional group, that would also work as a reasonable starting material to get you to your carboxylic acid. And then finally for this, we've got a methylating agent. So thinking about the starting material we need, so we can add a methyl group somewhere. Oxygen is a good place, and it looks like that's what has the methyl group added to it. So your best option for this would be your carbon double bond oxygen. That oxygen would have a negative charge on it. And now we have a nucleophilic oxygen which can attack this methyl group, and I'll just show the mechanism for that. It's basically an SN2 mechanism, one step to get us to that, and then plus sulfur with 2 methyl groups. All right, for the next one, we've got LSD, and we're asked to circle the diethyl amide functional group. So looking at the amide functional groups here we have an amine functional group. Here we also have an amine functional group, where this one's actually conjugated with this alkene. But for our amide functional group, this is it right here. So we've got our nitrogen attached to our carbonyl carbon. That nitrogen has 2 ethyl groups on it. So this is our diethyl amide functional group. Draw the reagents to convert the diethyl amide into a carboxylic acid. So if we're going to convert this into a carboxylic acid, based on the reagents that we saw on the last page, we need water, we need hydrochloric acid, we need an acid catalyst, and we need heat. So for the acid catalyst, this is important. We need to use this to protonate our oxygen, so our weaker nucleophile can actually come in, do a nucleophilic attack on our carbonyl carbon, and we can then eventually do some proton transfers and kick off our amine and eventually convert it to a carboxylic acid. One of these reagents, so of these reagents, we've got these here. This would convert that, so we've answered B. Would also react with a non-aromatic alkene. So looking at all of the functional groups in the compound, here we've got our benzene ring. Here we have a 5-membered ring. This is sharing electrons with that ring. So this is a situation similar to naphthalene, but all of these are aromatic. Our non-aromatic alkene is this one here. So this carbon-carbon double bond is non-aromatic. In this case, if we have water and hydrochloric acid, this alkene is actually more likely to be protonated than my alkene that was in that previous problem set, this one, because we can actually form a pretty stable carbocation intermediate. So once we protonate this alkene, so let's just show the mechanism here with some hydrochloric acid, which was in solution. That'll get us to a so this was my alkene here. I'm just going to draw part of the molecule. But once I protonate this alkene, I'm going to put the hydrogen on this carbon here. So that carbon right there now has 2 hydrogens. And this carbon right here is my carbocation intermediate. So from this carbocation, then we can add something like water or Cl-. Water is in more abundance, so most likely that's going to end up being water added, so we would form an alcohol functional group from that. So redrawing this, drawing the resulting product showing both functional group transformations. Redrawing this, here we have a 6-membered ring, we've got nitrogen there, that's there. That's no longer a double bond. This ring is fused, so we've got another 6-membered ring here. And then this 6-membered ring is also fused with a 5-membered ring right here. And those are both fused with a 6-membered ring right here. And we've got double bonds. I don't know why that line drew right there. All right, we've got our double bonds there, there, and there. This here is our nitrogen, which has a hydrogen attached. We've got a double bond there. This 6-membered ring, everything's fine there. That nitrogen's there. To be stereospecific, we need to specify this hydrogen here is on a wedge. So that's there. And then coming up from here, now we do not have our amide anymore. Now we have a carboxylic acid. And here we've got that hydrogen going in the back still. That's all there. And then on this carbon right here, now we've added, and I'll be flexible with what I see here, but something like either chlorine or better yet, an OH group. So most likely if we've got mostly water under acidic conditions, probably we're going to add an alcohol functional group to our alkene. So both functional group transformations, we've converted our amide into a carboxylic acid. We converted our alkene into an alcohol. All right, for this, draw the products and explain why the carbonyl carbon was not attacked. So based on the chapter we've seen, we really want to lean towards attacking that carbonyl carbon. This is basically saying it's not. Our nitrogen is relatively basic, and that's a very acidic proton. So in this case, we're going to do a proton transfer reaction, and we will form our carboxylate anion, and that will form a ionic bond with the protonated form of nitrogen, which is NH2 plus with 2 ethyl groups. So that is the salt that we formed. The carbonyl carbon wasn't attacked because essentially we formed the conjugate acid of our nitrogen, which is no longer a strong nucleophile. So we formed a fairly stable salt in and of itself in terms of this interaction, and then also our nitrogen is no longer nucleophilic. For the next one, methoxide was added to the epoxide, an organic solvent. Draw the mechanism and products of the reaction. So in this case, if we have a strong nucleophile, we're going to attack the less sterically hindered side. We're going to break open our epoxide. That'll get us to our intermediate, where now we have our oxygen with a methyl group attached. We broke open that carbon-oxygen bond, but that oxygen is still connected right there to that carbon, and now it has a negative charge. We still have our methyl group right down there. So this was the first step. This is what I was looking for 4 points, and then for extra credit, if we don't have HB in solution, we don't have anything that can protonate this, and we add our ethyl bromide instead, so we've got an alkyl halide now. We have a relatively strong nucleophile, strong base. This is going to act as a nucleophile in this case because we've got our primary alkyl halide. So we're going to do a nucleophilic attack on that carbon, kick off our bromine, and that's actually going to get us to our final product, which our MEO is still there. That's bonded out. We've got our oxygen. Now our oxygen has an ethyl group attached to it. So this is the final product. We've added our methyl group attached to an oxygen, which is now connected to that carbon. So when I say that carbon, we're talking about that carbon right there. Is that carbon right there? That's still bonded to this carbon right here, which still has that methyl group on it. It still has an oxygen attached, but now instead of forming an OH group like we usually did in these epoxide reactions where we had a nucleophilic attack on the epoxide, now we actually did another reaction. We did an SN2 reaction to form an ether.